Hello and welcome to episode 4 of Chemistry in 15 Minutes or Less. My name is Audra and this review lesson is on chapter 21, Nuclear Chemistry. First we need to talk about what's true in most experiments. The results are independent of the isotopes present and most influence is in the valence electrons. However, what's very important is that this is not true in nuclear chemistry. We're also going to start off with a couple of definitions. Nucleon and nuclide. A nucleon is any particle that makes up the nucleus. Basically, these are protons and neutrons. And a nuclide is any combination of protons and neutrons in the nucleus. So this is basically the way of saying nuclei without saying it, for lack of a better way of explaining, I guess. Another thing to mention is that atoms are held together by a strong, very, very close-range nuclear force. That is what holds together a nuclide. One of the most important topics that we're going to talk about is theoretical mass. Now, theoretical mass is calculated using the mass of protons, neutrons, and electrons, respectively, multiplied by how many there are present, and then added together. Theoretical masses are as follows for protons, neutrons, and electrons. Now, as you can see, protons and neutrons are very, very, very close in their theoretical mass, while an electron is much, 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 much less. Overall theoretical mass is always larger than the actual mass. The lost mass is actually the energy that is used to create the nuclear force that binds the atom together. Now what you need to do with this is calculate the mass deficit, which is where you take the theoretical mass that you calculated minus whatever the actual mass of something is. That will give you your mass deficit, which you usually draw as the Greek letter delta, and then M for mass. Should be the lowercase one. Now, we also need to talk about energy equations. A very recognizable energy equation is E equals mc squared, where E is your energy, m is your mass, and c is the speed of light squared. Now, the speed of light, this is a value you will need to memorize, is 3 times 10 to the 8th. We'll talk more about that in a later chapter when we actually talk about light. But the other really important subtopic other than theoretical mass is radioactive decay. Basically, radioactive decay is spontaneous disintegration of a nucleus into a slightly lighter nucleus accompanied by particle and/or electromagnetic radiation emission. This is a way for unstable nuclei, which is everything past bismuth on the periodic table, anything greater than 83, with an atomic number I mean, is unstable. It needs to become stable, so it slowly moves back down to being stable by releasing particles and changing its nucleus. Protons repel each other, so all stable nuclides have to contain neutrons, except, of course, for protium, which is the version of hydrogen that only has one proton, no neutrons. Some other definitions that we need to talk about are positron, which, for all intensive purposes, is an antiparticle to the electron. It has the same mass, but has a positive charge. An alpha particle, a beta particle, and a gamma ray. An alpha particle is basically a helium-4 nucleus. That means it has 2 protons, 2 neutrons. A beta particle is pretty much an electron. It's almost impossible to tell the difference between these, so don't try to. And a gamma ray is an ultra-high energy form of non-visible light. While we're talking about those, I'm going to draw you a quick little table that is going to include the type of particle, its charge, symbols that it includes, and I'll tell you what it's stopped by. So we are going to talk, as far as particles go, proton, neutron, beta particle, positron, alpha particle, and gamma ray. Now, a proton has a charge of +1, and its symbol is usually a P+, or can also be symbolized as a 1/1p, which you might remember from our last lesson. A neutron has no charge, it is a neutral particle, and it is usually set with the symbol of n with a 0, or 1/0n. A beta particle has a charge of -1, and its symbol is another Greek letter. I don't remember how to say it, but it looks like a B, and it can also have numbers associated with it like the other ones. Or you can also write it as an electron. Like I said, they're basically the same thing. A positron has a charge of +1, and is symbolized very similar to a beta particle, except with a positive charge. Now, an alpha particle has a +2 charge, and can be symbolized either with another Greek letter that looks like an A, or as I said earlier, the helium-4. Now, a gamma ray also doesn't have a charge, but that's because it's not really a particle. It is symbolized by another Greek letter that looks very similar to an uppercase Y. Now, as far as what can stop these types of radiation or emission, a proton can be stopped by paper. It doesn't take very much to stop it because it's pretty big. And a neutron has to be stopped by something that's about 1 centimeter of lead, which means it can pass through more than a proton can, but that's probably because it doesn't have a charge. A beta particle can be stopped by aluminum foil, and so can a positron. An alpha particle can be stopped by skin and paper because it's so big, but a gamma ray requires large amounts of lead to be able to stop it because it is so small and so fast. As far as equations go, you should have those in your notes. I don't really need to write them out, and I have limited time, as I said, in every single one of these episodes. But they're pretty easy to figure out because whatever molecule or atom you start with just ejects a particle. I do need to talk about half-lives as well. A half-life is the amount of time required for half of the radioactive nuclide to decay. So half of whatever the substance is. There are two ways to do this. You can do this in the equation n equals n0 times 1/2 to the xth, where x equals t divided by t1/2, where t is the amount of time that it sat out, and t1/2 is the actual half-life. The other way you can do that I personally find easier, is through this table, where you have your mass in whatever units, by time in whatever units, and the number of half-lives here on the end. Because this table can be used to find any three of these depending on what you have, you just fill them out going down. Radioactive materials do have a couple of practical uses. They are used as tracers in medical procedures, where they can be detected by machinery. It's why you sometimes have to take a fluid before going through some sort of medical test, or it's also how carbon dating is done. The final thing to talk about is nuclear fusion versus nuclear fission. Now, fusion is the merging of two atoms into one. This is what's done in stars and in the sun, where a couple of hydrogen atoms are compressed together with enough heat and energy that they combine to form helium. Nuclear fission is when you split large nuclides into smaller ones. This is what is done in nuclear power plants, where very large, unstable nuclides are bombarded with other particles until they break into two smaller nuclides. I know this episode might have been more brief and a little more gloss over things than some of the other ones, but that's because we didn't spend too much time on it in class, and I'm hoping it won't be as important. Plus, my notes are pretty brief because I missed some time in this section for a band trip. However, this should conclude episode 4 of Chemistry in 15 minutes or less. Feel free to leave questions or suggestions in the comments below, and be sure to follow the in-video links, check out the playlist, or head over to my channel for more videos on chemistry review. As always, I hope this helps, and I hope you have a great day.